Hello everyone, Jason Cormier from OddBike.com here with something a little more esoteric than usual today on the OddBike YouTube channel. This is the first video of a new series here on the OddBike YouTube channel called OddBike Tech, where I'll be sharing in-depth technical information, how-tos, and anything else that might be too boring for your typical fluffy clickbait video. So for our introductory video here on OddBike Tech, I'm going to be talking about tuning Ducati motorcycle fuel injection. Specifically, I'm going to be looking at covering Magneti-Marelli systems from the late 1980s to the early 2000s. So this will include the P7, P8, and 1.6M systems that you're going to find on Ducati 851s, 888s, 916s, 996, 748, ST2 and ST4 most commonly. You can also find variants of this system that were used on some Moto Guzzis like the V11 and some very early MV Agusta F4s. I started tuning this system on my 1.6M 916 and I learned a lot through the process. So I wanted to share some of that knowledge to spread the accessibility of this type of tuning for older Italian bikes. In the past 2 years, these systems have become thoroughly decoded and reverse engineered by independent tuners and tinkerers, which makes adjusting this system more accessible than it's ever been. That being said, you do need to dig pretty deep in the forums to get most of this information, so that's where I wanted to give a brief but detailed overview of the system and the procedures to help shade tree mechanics like myself learn how to do it themselves. Magneti-Marelli fuel injection system in these bikes is pretty basic. That makes it easy to figure out and understand, but it limits the precision and the adaptability you're going to find in more powerful systems. Specifically, these ECUs use what's called alpha N EFI programming. In essence, this means that the system is completely open loop. Alpha N is the most basic of the three main types of fuel injection tuning. Alpha N referring to alpha throttle angle and N RPM. Those are the two basic readouts that are used by the computers to look up values in a table and determine what it's going to do. And that's it. There's no oxygen sensors, there's no airflow sensors, there's no closed loop operation. It does everything based on what is programmed in the computer. This is in contrast to speed density or mass airflow tuning, which use sensors to determine the amount of air that's actually going into the engine, and then determining how much fuel is going to need to be mixed with that air at the combustion process. And then closed loop being something that can read the oxygen levels in the exhaust with obviously an oxygen sensor and determine adjustments to fueling on the fly. Alpha N doesn't do any of this stuff. The fuel and spark of the system is based on the maps that are programmed in a replaceable EEPROM chip that's inserted into the ECU. The EEPROM setup means it's really easy to program multiple maps and swap the chips to test your changes without having to hook up to a computer. However, the EEPROM contains only one coded map and that's it. So to change anything, you need to erase and reprogram the chip. There's no on-the-fly adjustments. So to get started with this, you're going to need four things. You need the editing software, you need the chip burning hardware, you need some spare chips, and you need some base maps to edit and build off of. So the program that I'm using here is called Tuner Pro. It's a very powerful tuning tool that was originally developed for automotive applications, and I've had really good success with it working with Ducati stuff on here. But to use Tuner Pro, you need to find a file that will actually decode the programming of the maps that you're putting into it. So specifically, what you're looking for is an XDF file. And I'll include a link below in the description text to some XDF files for the most common types of ECUs. But that is your baseline to get started with Tuner Pro. And then after that, you're going to need to get a bin file. So the bin file is the actual mapping file, and that is what you're going to be tuning. Now, the bin file is written hexadecimal, and the reason why you need an XDF file is because it's just a jumble of hex code that you would be very hard pressed to figure out where the maps are and what their values are. So suffice to say, it's a lot easier when you have an XDF file, which basically decodes everything and arranges it into tables that are easy to figure out and easy to edit. So now this all brings us to the hardware, and what I'm using is the Moto Burn 2, which is pretty inexpensive and has served me really well. Burn 2 comes with Moto's Flash and Burn program, which makes it really easy to copy, erase, and program the whole range of EEPROM types, including the ones that we're going to be using in our bike. And when you buy the Burn 2, you are given a couple of spare chips to work with. Now we can start to have a look at Tuner Pro and look at the tables that you're going to be editing. I'm using a basic XDF that sticks to the essential tables without opening extraneous stuff I don't really need to mess with. You can find more detailed XDF files if you want to delve into more of the programming, but for my purposes of just adjusting the fuel and spark and some of the trim tables, this is more than good enough for me. So the three essential maps that you're going to be working with are the base fuel map on the horizontal cylinder, the cylinder 2 delta fuel map, which is the vertical cylinder, and the base ignition map. So for the fueling, you start with the base map on the horizontal, aka front cylinder map. And this is obviously Ducati specific. This is your base value for both cylinders, because what happens is that the delta map, seen here, simply takes the values off of the front cylinder map and alters them by a certain amount. In this case, they're both read in milliseconds of injector opening, and the delta map is adding or subtracting X amount of milliseconds to the front cylinder map. So the rear cylinder map is directly based off of the front cylinder map. So in essence, it is two maps, and they are separate, but one is directly tied to the other, and they need to be edited together. You cannot edit them independently. So any change that you make on the front cylinder map is going to automatically apply to the rear cylinder map, regardless of any previous changes you've made to it. All the values here in these fuel maps are read in milliseconds of injector opening time. So the system is going to provide a constant amount of fuel pressure that's mechanically regulated. So in the case of these Ducatis, you have a fuel pump that runs at a set rate. There's no varying duty cycles like you find on some later bikes and on some cars. You have a set fuel pressure that's constant. So these values are going to be pretty consistent. There's no variability if the fuel flow is relatively constant, which it is in theory. So for all these tables, the layout is basically the same. So you have RPM on the vertical axis, and you have degrees of throttle opening on the horizontal axis. And then any point between them is what the computer is actually going to be referencing. So for example, if we look at this value, at 5,000 RPM and 28.9 degrees of throttle opening, the computer is going to provide 7.42 milliseconds of injector opening, ergo 7.42 milliseconds of fuel. Now for spark mapping, we only have one ignition advanced table. There's no provision for knock control or variable spark timing in the system, so what you see here is what you get. You should know that what you're looking at is, again, you have RPM and throttle position, and you have degrees of timing before top dead center for when the spark plug is going to get fired. So thus the final value of any of these calculations is going to be the base map plus or minus the trims that is provided by the temperature and barometric pressure sensors on the bike. And that's it. Those will determine your final injector duration. Now, on a closed loop system, you're going to also have oxygen sensor feeding back into it, or on an airflow based system, it's going to be reading the amount of air that's entering through the air box or through the intake or the throttle body and determining the mass of fuel that needs to go along with it. You don't have any of that with this. The only trim factors are with regards to temperature and air pressure, which is actually barometric atmospheric pressure, so just going up and down in altitude. And all of these are blanket changes. So you'll see, for example, if we look at our air temperature correction, this is in degrees Celsius. So at 17 to around 20-ish degrees Celsius, there's zero correction. But once you start going up to say 29, 30 degrees Celsius, then there's a correction applied of minus 1.56. And that means minus 1.56%. So it applies a percentage-based alteration to the entire map. It's not based on milliseconds, it's a percentage-based calculation. The same goes for the air pressure trim and the engine temperature corrector, which is just coolant temperature in the case of these Ducatis. In a Moto Guzzi, it would be oil temperature correction. So there again, it's enriching or leaning the system overall based on these three sensors. And that is the only correction that is applied to your base map. So your base map is going to be that value plus or minus this value, plus or minus this value, plus or minus this value. And that, after everything has been done, you come up with your final value that is actually executed by the computer at the injector. Now, to actually make useful changes, you're going to need to have some way of verifying your results. So this means that you're either going to be putting the bike on a dyno and measuring the air-fuel ratio at the tailpipe, or you're going to be installing a standalone AFR gauge and a wideband sensor on the bike, and you're tuning it on the road. I did a combination of both. I started messing around with seat of the pants stuff, then I ended up verifying some of my work on an inertial dyno, dynojet type dyno, and this turned out to be a pretty big waste of time. I didn't have enough time I didn't have enough dyno time or money for endless hours in the room, and the inertial dynos are only useful for doing wide open throttle pulls, because you can't load the individual ranges to get meaningful data unless you have access to an eddy current or a brake type of dyno, and you have lots of time to work your way through all the load ranges along the RPM scale. So for me, what I ended up doing was I bought an Innovate Motorsports MTXL standalone wideband gauge. I welded some bungs into the front and rear headers of the bike so that I could read each cylinder individually, and then I ended up hooking up the gauge on my dash. So this way I could go and make notes while I was riding and gradually adjusting each range to get the AFRs right into my targets. So this is a really time-consuming and tedious way of doing it, but the results are really worth the effort. You also get the benefit of real-world load, ram air, and environmental variables on the road that you won't be able to recreate on a dyno easily. And that's assuming you're going to be willing to invest hundreds, if not thousands of miles and many hours of small tweaks to get things perfect. For a 4-stroke naturally aspirated motorcycle like this, I target 3 basic AFR values. Now I'm assuming here that you understand air-fuel ratios and how to read them, because you're going to need to know that baseline before you start messing with the mapping. So for idle and cruise, I'm aiming for 13.5 to 14 to 1 AFR. The Ducati likes to be on a little bit richer side for cruising. If you're going any leaner than 13.5, it tends to make the throttle response a little too abrupt. Some bikes might do well to be around 14 to 14.5, but with regards to these Ducatis, stick to around 13.5. For the transitional zones, which is to say on the throttle above the cruising zones but below 3/4 to wide open, I'm targeting around 13 to 13.5 to 1. This will give you really strong part throttle torque and really nice throttle response without being too sharp or too abrupt. And once you reach the wide open range, so about 3/4 to wide open, you want to target about 12.8 to 1. This gives you a safe margin for extra load and gives pretty good torque and response. And now all of these numbers are approximate. You want to get as close as you can, but you can't expect to be bang on all the time, especially with an Alpha N system, with the variability that is built into the way it's mapped. The variability of the system and the way these older ducks run makes it pretty much impossible to be 100% flawless, but you can get pretty damn close with lots of work and small incremental changes along the way. Now you can squeak the horsepower readings a little higher on the dyno by running leaner than 12.8 at wide open, but on the road you're going to find that 12.8 feels better by the seat of the pants. It feels a little bit torquier and a little bit more responsive. Tends to be a little bit flatter if you try to run it a little bit leaner. And the difference in the horsepower is pretty minimal. I mean, when I was testing on the dyno, I think we were able to squeak it up like 3-4 horsepower just by leaning it out a little bit more than that into like the 13s. So there's really not much in it. Now, with regards to ignition tuning, it gets a little bit trickier. Now, if you aren't comfortable with messing with the ignition tuning, it's a good idea to just pick a proven base map and use the ignition map in it without alteration. Now, if you are comfortable with messing with the ignition, it's a lot of trial and error based on seat of the pants and also abiding by the knock threshold. So if you start knocking or pinging, you need to back off at least 2 degrees. You want to be 2 degrees below the threshold of knock at the minimum to be anywhere near safe. And you have to remember that with this system, there is no knock feedback and there's no way for the computer to protect the engine if it starts knocking. So if you hear knocking, you have to stop and correct immediately. It's also a good idea to smooth the transition between cells in the 3D maps. Sharp transitions will be felt as irregular torque on the throttle, and some really drastic shifts can induce knock just from the rapid timing changes. And we're going to examine that in detail when we look at the actual 3D mappings and how to adjust in Tuner Pro. General rules of thumb for ignition mapping is that you're going to see your highest values at light load and your lowest values at high load and peak torque. Cylinder pressure and the potential for detonation are highest at high loads from low RPM and at the peak torque, and that's why you want your ignition values to be the lowest in those zones. Now, one of the major downsides of Alpha N and any of these open loop systems is that the computer has no feedback for bad or incorrect conditions. Your job as a quote-unquote tuner then is to create a map that maximizes the performance but remains safe across the normal operating ranges. With the limitations of the system, that means you have to find the fuel and spark values that work best across a broad range. There's no per gear compensation with this mapping. That also means that there's no load compensation, then there's no compensation for the fuel density or the oxygenation of the fuel, i.e. if it has 5 or 10% ethanol versus no ethanol. So what this means is that if you tuned all of your values to hit your targets in first or second gear on a flat road, you're going to run lean once you go into a higher gear or once you're loaded up going up a hill. So that's where you need to be smart. You have to aim to hit your targets in fourth or fifth gear in varying conditions. And if you're able to nail the targets in those ranges, you're pretty safe overall. You'll just need to understand that you're going to end up showing slightly rich at lower speeds and lower gears as a result of that, but this is totally normal. You should also try to stick to one fuel source and one fuel type. That means that you're only running, for example, Shell 91 octane throughout the tuning process. You want to have maximum consistency, because switching fuels can alter the AFR in small but significant ways, never mind the whole octane versus detonation problem. For example, I found that if you're running E10 versus an ethanol-free fuel, you're generally going to see it about 3 to 4% leaner at the tailpipe. Now, with all of this being said, we're going to be getting into the actual adjustment. So in Tuner Pro, it's pretty straightforward. So you're looking at your table here. So we'll start with our base fuel map. So here you're going to see a value in milliseconds. And as we showed you before, it's going to be the intersection between throttle position and RPM. Now, you'll be starting with the base map that's going to have these values already populated, and you're going to be making adjustments based on ranges. So let's say we saw that in the cruising range between 3,000 and 4,500 RPM, it was running a little bit lean. So let's say it was running 14.5 to 1 and we wanted to see 13.5 to 1. Well, I've found that with regards to this particular system, usually a 5% change is enough to move the AFR 1 point. So that's to say, if we've got 14.5 and we want 13.5, what we're going to do is we're going to add 5%. Now, Tuner Pro makes this really easy. All you have to do is go up here to your function tab, and what you want to select is your multiply function, and then you're going to put your value in. So if we want to add 5%, what we want to do is actually put 1.05 to multiply, select the cells, hit execute, and bam, it does it for us. And the same goes if we wanted to remove 5%. So we would go up here. If I wanted to lower it 5%, I would do 0.95 and execute. So generally the amount of change that you want to make at any given time try to aim for 5% at most and work your way up that way. I'll even do like 2%, 2.5% for small changes just to dial things in. But generally, if you're making a shift of more than 5%, it's going to get harder to kind of determine where you're going. So 5% at a time is a good maximum. And you're going to have to go back and forth where you're going to probably have to do one and then a second application, or you may have to do 5%, then 2%, et cetera, to really dial it in. This is where it gets really tedious and time consuming, and where it's critical that you have a really accurate air fuel ratio gauge. Now, the most important ranges that you're going to be looking at are essentially here, here, and here. So that is basically the middle part of the map. That is where you spend 90 to 95% of your time. You don't spend much time at high RPM, low throttle opening, and you don't spend much time at low RPM, high throttle opening. So the majority of your time you're spent right in the middle, where it's part throttle, it's full throttle at higher RPM, and it's cruising in the mid-range. Rarely are you going to be cruising at 10,000 RPM. So in the areas where the values aren't really as critical, so specifically up here and down here, you just want to have a general safe value. Once you've got these kind of in the ballpark, you don't have to really fine tune them to the nth degree and trying to find that last percentage, because you're never going to be in these ranges, especially these really low RPM, high torque ranges where you don't want to be going full throttle from 2000 RPM. That's just lugging the engine, and that's bad. So you just want to have safe values here, and then you really want to focus on tuning the middle, because that's where you spend most of your time, and that's where it's critical to get things right. You're going to notice that you're always going to have your peak fuel at peak torque. So in the case of my engine, that is at 7,000 RPM. And you can see this if we look at the three-dimensional graph, which is here. So this is the main horizontal fuel map in 3 dimensions, which is a really handy tool in Tuner Pro because it allows you to visualize the different ranges and how the fuel is scaled, and see if there's any weird things going on, any weird transitions, any holes or peaks or valleys in the actual fuel map. You can see that this is a little bit strange, that at about 3,500 RPM I have a huge spike in the fuel, and that's because with my current setup with SPS cams and high compression pistons, for some reason it needs that much fuel at that RPM when you're going full throttle. Reason being, I'm not entirely sure. It could have something to do with accelerator enrichment or tip enrichment not being able to keep up. I didn't really have that much of a problem before I started hot rodding it. Before then, this was relatively flat, and it didn't really start peaking until 7,000 RPM. Now, in a perfect world, both cylinders would be perfectly identical and they wouldn't have to have any change between them. But obviously theory is a lot different than practice. So what you end up with is on the delta map, you're going to have zones that are both negative and positive, and sometimes right next to each other, and sometimes in pretty significant amounts. I tuned both of my cylinders individually, so I started by tuning the front cylinder on its own with the wideband sensor inserted into the front header. And once I had all of this dialed into where I wanted it, then I switched to the rear map and I made the corrections so that I would still get the same targets out of the rear as I did on the front. And it ended up that in some spots there's something like 10-15% difference between the front and the rear, either positive or negative. So there's not a lot of rhyme and reason to it. It's, as I say, it's due to exhaust tuning, intake tuning. You will see that delta fuel maps will vary from bike to bike, and to get the best results, you're going to want to tune it yourself. I found that doing this and getting everything dialed in on both cylinders actually made a significant difference in the throttle response and probably added quite a bit of horsepower in the mid-range. It was quite significant what the difference was between a zeroed delta map and a perfectly adjusted delta map. and it ended up being completely different from any of the base maps that I had a look at. With regards to the trims, you probably won't have to adjust any of these. I have had to adjust some, in my case, the engine temperature corrector and the air temperature corrector, mainly because I've been running different fuel pressure regulators. I've gone back to a 3-bar pressure regulator, which is what is stock on the 916 and 996 models. For a while I was running a 4-bar Harley-Davidson regulator to try to get a little bit more fuel out of it, and that was before I switched to a double injector setup to feed this hot rod engine I'm running. And I did have to make a few little corrections. Again, these are percentage based, so it's fairly easy to figure out that, okay, well, if I find that it's going a little bit too lean in the hotter zones, well, I just want my corrections to be a little bit higher, in that, meaning that it would be -1 instead of -3%, or vice versa. And it's the same for all 3 of the corrections. So air pressure being barometric pressure, engine temperature being coolant temperature, and air temperature being ambient air temperature. But most of the time you won't have to mess with these, particularly if you have a pretty good base map. One to watch out for is the air pressure corrections. Some of the Ducati base maps have simplified the air pressure corrections a lot, meaning that they do not compensate it as much at the lower pressures, meaning higher altitudes. And that was a safety thing, so that if the air pressure sensor failed and defaulted to a standard value or defaulted to a high value, it wouldn't end up, you say, pulling 40% of your fuel out, as you can see here. Now, if you're comfortable with having those correction factors available and you're not dumb enough to ride your bike like an asshole when the pressure sensor fails, because you'll notice when it does, then you can run more aggressive corrections here than Ducati was offering from the factory. And that's particularly important for someone like me, because I live at 3,500 feet of altitude above sea level, and I do a lot of my riding between 5,000 and 7,000 feet up in the mountains. So having a really good barometric pressure trim is crucial to getting everything really consistent and working well across the broad ranges that I end up riding in. Now, for adjusting the ignition mapping, you're not going to want to necessarily use the multiply function. You're going to want to use the offset function. So what offset does is it's plus or minus whatever value you put in. So let's say I wanted to add 1 degree of ignition advance in this 21 to 25 degree range here. So what I would do is I would select offset. I would put a value of 1 and execute. Sorry, it actually went straight to the 3D map, but you can see it's adding 1 degree at a time every time I hit that. And you can do the same in the opposite. So if you hit -1, it'll take a degree out every time you execute. Now, if you find that your ranges are a little bit difficult to tune in, so let's say you have a particular problem at 6,500 RPM. Well, the way I have my tables laid out, I have 6,000, I have 7,000, I don't have 6,500. But I can easily change that 6,000 or 7,000 into a 6,500. I just need to go into my RPM points. There, I can set whatever value I want, and that will then be applied to the maps and change the scaling of the table. I usually try to stick with a fairly broad range unless I'm having a particular headache in one specific zone that I just can't seem to tune between 2 of the map values, and then I can go a little bit finer resolution. But you can't add any more lines or cells to this table. It's a 16 by 16 table, and that's it. So you have to be able to work within that. And the same goes for your throttle position values. If you wanted to add a value at, so say here I have 10 degrees and 12 degrees, or 12.5 degrees, well, maybe I want a value at 11 degrees because that's where I'm cruising all the time. So I can then change that to an 11 or what have you. This is also how you're going to set your RPM limit, aka your rev limit. It's through the actual RPM points. So I have mine set at 10,500, fairly conservative, and I do that because I'm peaking horsepower right around 9,000 and I don't need to go much higher. But if you say wanted to set it to 11,000, well, all you have to do is change your value right there. Now your red line is 11,000 RPM. So use that with caution, obviously. So now that we've seen the basics of actually adjusting with Tuner Pro, and these are the basics. I do recommend that you do a little bit more research, check out how to work with Tuner Pro and some of the functions that are in it, because it's a really powerful tool. Well, let's say now you actually want to burn your chip. So now we're actually going to go into Mote's Flash and Burn. So I have the Burn 2 connected right now, and I do have a chip in it. So the first thing we're going to do is we're going to make sure we have the right chip supported in the supported chips list here. And in this case, it's a 27SF512. And what I want to do is I want to erase the chip to start. You always want to start with a blank chip because you cannot overwrite a value that's already on the chip. So start by erasing the chip, then do a blank check. You can see here it has checked and it is blank. So now we're going to load a file to our buffer, which is to say that we're just going to open a bin file that we want to burn. So I want my 3-bar SPS map here. You can see it's loaded. Then you hit Program Chip. Once it's programmed, hit Verify, just to ensure that everything's okay, to make sure that you inserted the chip correctly, that it was cleared before it actually got programmed, because you can, if you have an error, it will just show programmed, and if you don't verify it and you stick it in the bike, it may not actually run until you've verified that it does in fact match the buffer file. So here you can see success verification succeeded, we're good to go. Now, let's say you have something on the chip that you actually want. Well, then you can actually save buffer. And what that is, you start by reading the chip. Then you're going to save buffer to file. And when you do that, you're actually taking the data that is on the chip and saving it into a bin file on your computer. So that's how you can rip a map off of an existing EEPROM that you may have if you want to start with that as your base map, or if you want to get a backup of something you've done previously. So I hope you enjoyed this inaugural video in the OddBike Tech series here on the OddBike YouTube page. Thanks for watching, and I hope that you learned something about Ducati fuel injection and how to adjust it for those 5 people out there in the internet that are interested in how to do it. If you like this type of content, be sure to like, share, and subscribe to the YouTube channel. Check out odd-bike.com and visit our Patreon page to contribute to the ongoing OddBike project. Thanks for watching.